In this video, we'll be looking at some basic principles of structural design for the structures. For the design of any structures, we have to make sure that we meet these four prime structural design requirements. They are: the structure has to meet serviceability requirement, it has to meet the strength requirement, durability requirement, and the structure has to be economically feasible as well. Let's go through each one of them now. The structure has to be serviceable. By serviceability, we mean during the day-to-day life of the structure should be functional and it has to satisfy all the functional requirements it is designed for. By functionality, it also means that it shouldn't cause any discomfort to the occupants or the users of the buildings as well. For example, the structure, if we are designing, should not have any excessive deflections or vibrations, or if it is reinforced concrete, it shouldn't have any excessive cracks as well. For example, if you are staying inside a building and the beam of that building has an excessive deflection, there is a large deflection, as an occupant, you will not feel comfortable to stay inside that building. So that means that the structure doesn't meet the serviceability requirement. The structure might be perfectly fine from strength perspective, but it doesn't meet the serviceability requirement. Similarly, if the structure has too much vibrations, occupants may not feel safe or comfortable, and it doesn't meet the serviceability requirement as well. The London Millennium Bridge is a shallow suspension bridge, and it's of 300 meters long and has 3 spans. It is a pedestrian bridge, but when on the inauguration day, as many people walk on the London Millennium Bridge, the bridge had a excessive swaying or vibration in the bridge, which caused big alarm for the users, and the bridge had to be shut down, and they had to use some remedial measures to control the vibration in the bridge. Let's have a look at the video of that bridge and see what actually happened then. You can see on the inauguration day, a lot of people walked through the bridge, and now you can see the swaying of the bridge, and which was obviously causing discomfort to the pedestrians on the bridge. There is quite a visible shaking in swaying of the bridge. Structurally, the bridge might have been okay, there was no issue structurally, but the excessive vibration in the bridge definitely didn't meet the serviceability requirement of the design. The structure has to meet the serviceability requirement as well. In the day-to-day loading of the structure, for the day-to-day use of the structure should not have any excessive cracks or excessive deflections or excessive vibration that will cause discomfort to the occupants. And also, the excessive deflection in the structures can also damage the partition walls on top of it, or it can cause problems in the doors and windows as well. Another absolute requirement for the structure is that it has to be strong enough to take all the force it is meant to take. Not only just the day-to-day loading, but also during the extreme loading conditions, the structure has to be strong enough to withstand those forces, and that's the absolute requirement from the safety of the structure and safety of the people or the users of the structure itself. Recently, there was a tragic collapse of Morandi Highway Bridge in northern Italy in 2018. It is a reinforced concrete bridge, and during the torrential rain in Italy in August, the bridge suddenly collapsed, killing more than 26 people. So you can see the collapse of the reinforced concrete bridge here. It is a cable-stayed bridge, and it was constructed in 1960s, and it was quite an old bridge, but when it collapsed, there was no warning. It happened very suddenly. So that we have to make sure that the structure is strong enough to take all the forces, even the extreme forces that it can that it can be subjected to in its life. The third condition the structure has to satisfy is the durability. By durability, it means that the structure should not have any rapid deterioration or degradation throughout its service life. It has to be strong enough, it has to serve its purpose during its service life period without any rapid deterioration. And the structure can maintain its function without the need of any undue maintenance or repair during its service life. And that's what durability is. This is an example of a pre-stressed concrete bridge in Japan. The bridge is located near ocean, so it is a very extreme marine environment. Especially for the structures like reinforced concrete structure, the marine environment, the salt in the ocean can lead to the corrosion of the reinforcements or the steel inside the concrete, and that's what happened in this bridge. As you can see, the concrete has come out, and the steel inside it is a pre-stressed steel that are exposed to the elements, and they started deteriorating, they started corroding, and once the steel breaks, then the structural integrity is compromised. So they had to replace this bridge, they had to completely demolish the bridge and construct it again, the new bridge. So this is what happens when the structure does not meet the durability requirement. It will eventually compromise the structural integrity itself. So the structure has to be durable enough so that there is no rapid deterioration or degradation throughout its service life. So we have to make sure that we take proper measures when we are designing the structure. We have to take proper measures that the durability conditions are met as well. And finally, the structure we are designing has to be economically feasible as well. If it is not economically feasible, then we probably cannot finish the structure, or we cannot justify the structure. So whatever the structure that we are designing, it has to be economically feasible from material perspective, from construction perspective, or labor cost perspective. It has to be economically feasible as well. This is an example from Bangkok in Thailand. In 1990, there was quite an ambitious project in Bangkok to construct the Hopewell mass transit system for the vehicles and the train to connect the city to the airport there. But the project never could be completed because of the economic reasons. There was a financial crisis during that time, and it could never be completed. And you can see that around 500 of these concrete pillars were lying there for more than 15 years. I was there in Bangkok. I did my master's from Bangkok in Thailand, and we could always see those big stone pillars lying there. It was quite a bit of eyesore there when you're traveling through that highways. They are often called as Stonehenges of Bangkok. So again, if you are going for an ambitious or any project, any structural engineering project, design project, you have to make sure that your design is economically feasible so that you can complete it within the given resources and time as well. And to make sure that these serviceability, strength, or durability criteria are satisfied, we have standards, design standards. And we make sure that we are designing according to those design standards. In Australia, we have Australian standards, and for structural design, we have these Australian designs code that are relevant to us. So AS NJTS 1170 is a design code that takes into account the structural design accents, that takes into account all the loads and the load effects that the structure can sustain. So it has different parts from part 0 to part 4. The part 0 is for general principles on how to calculate the structural design actions, the loads. Part 1 deals with the dead load, permanent load, and other actions, and the live load. And part 2 deals with the wind action. And part 3 and part 4 deals with the snow and ice actions. And part 4 is for earthquake loading in Australia. But for this subject, we are mainly concerned with this three of them, that is part 0, part 1, and part 2. So please download these codes from Standards Australia through the JSU library. It is free again, and you have to print it out because you need to bring them into the lectures and also tutorials, and also you are allowed to take them into the exams as well. So print it out if you haven't yet, and bring it to the lectures from now on. And as we go on, for the steel structure we use Australian standard AS4100, and for the timber structure we use Australian standard 1720.1. So we'll come to that one as we start teaching steel and timber, but for now you need to have at least 1170.0, 0.1 and 0.2 downloaded and ready to use. Now the structure you are designing, whether it's a bridge or a building, it can be subjected to many different kinds of loading. Obviously one loading that any structure has to withstand its own weight as well, because we are using a very heavy materials like steel and concrete, so the structure has to withstand its own weight, right? So that is called as a dead load. The dead load basically means the permanent weight of the structure, or anything that is permanently acting on the structure is called as the dead load. It can be the weight of the material itself, it can be anything, any fixtures that's permanently incorporated into the structure. And the second type of loading that the structure can be subjected to is live load. Live load is a variable or sustained load that can act on a structure over the period of its service life. It is not constant like dead load, but it can vary. So for example, if it is a stadium, the weight of the audience of the stadium is the live load. If it is a car park, the weight of the cars on the car park is the live load. And live load can be variable or sustained as well. Some part of live load, like furnitures, can be sustained over a bit longer period of time, whereas like people or cars, it will be variable. It will be there for a very short period of time only. And the structure can be subject to other kinds of loading, like a snow loading, wind loading, or the earthquake loading as well. So we have to design a structure in such a way that it can withstand all of these different kinds of loading it can be subjected to during its service life. The first important loading that we have to take into account while designing a structure is the dead load. As I said, dead load is basically any permanent loading acting on a structure, that it includes the weight of the structure itself, the self weight of the structure, and weight of all the materials permanently incorporated into the structure. So for example, if you're designing a reinforced concrete building, we have to take into account the weight of the concrete itself, weight of the concrete slabs, columns, beam. We have to take all of that into account while designing the structure, and they are termed as dead load or permanent action, and we denote it as G in AS 1170.1, and that's where we get the details about the dead load. And of course, the structure has to be strong enough to withstand its own self-weight. This is a collapse of steel structure under construction in Texas in 2015. It is a steel structure. It was just under construction when it collapsed, so there was no any external load like wind or earthquake happening at that time. The structure wasn't strong enough to withstand its own self-weight from the roof and from the steel members that it was built with. So let's have a look at the video from here.
As investigators work to determine what caused a practice facility under construction to collapse, the Argyle School District released surveillance video of that fall. One worker was killed, 3 others injured on April 2nd when the structure near Argyle High School collapsed. Fox Sports' Phil Alvarado has more now on this newly released video. Phil.
Heather, the day of the collapse, there were strong winds in the area, and you can see that in the trees when you watch the video. The metal frame appears secure until one end of it starts to fail.
The collapse of the indoor activity center seems to come without warning. Every bit of the building's metal frame hits the ground in seconds. It is captured on security camera video from 4 different angles. The building was under construction next to Argyle High School. 1 man died in the collapse. 5 days later, a second worker was run over by a truck and killed at the same site. The Argyle ISD is doing a safety audit of all its construction and renovation projects. The district says it thoroughly vets all contractors. Argyle Superintendent Talina Wright says the safety audit will add another level of standards to our vetting process for future construction projects.
Now, to calculate the dead load of the structure, we need the densities or the unit weight of the materials, and we need the volume of the member as well. So with that, we can find out what is the total weight of that structure or the structure member. For that, for the AS 1170.1 gives us in Appendix A, it gives us the unit weight of different kinds of construction materials. As you can see here in this table, please look at 1170.1 in Appendix A. You can see the in table A1, you can see the unit weight of different construction materials. As you can see here, the most commonly used construction material, concrete. The unit weight is 24 kilonewton per meter cube if it is a plain concrete. And if it has a reinforcement in it, we usually use 25 kilonewton per meter cube. And for steel, we have 76.9 kilonewton per meter cube is the unit weight of steel. And for timber, we can see the depending on the species of timber, your unit weight can vary between 5 to 9 kilonewton per meter cube. So once you know what is the unit weight of a material and the volume of your structure member, you can calculate what is the self weight of the member, and then you have to use it, incorporate in your design. And as we discussed before, apart from the self-weight, the structure is also subjected to the live load or imposed action as well. A live load is basically a variable action resulting from intended use or the occupancy of the structure. So again, if it is a classroom, it is the weight of the students. If it is a car park, it is the weight of the cars that we have to take into account. Part of the live load can be sustained, like furnitures. It can be sustained for a certain period of time, or it can be variable like cars or people who might be there or not. Now this is another tragic collapse, and it is mainly because of the live load acting on the structure. In 2018 in Indonesia, there were some college students visiting an Indonesia stock exchange, and as you can see, the hallway is a bit crowded with the students, and because of this extreme live load conditions, the hallway gave away and it fell down. And we can have a look at this video. The visitors of that building, they are considered as a live load, and when there was extreme live load acting on that particular area of the building, the structural members couldn't withstand those extreme loading condition, and the building hallway fell down. Now, to calculate the live load for different types of structures, AS 1170.1 table 3.1. So if you look at the table 3.1, it gives us a guidelines on how to calculate the live load for different types of structure. Basically, it has divided the different structures into 7 different kinds, and depending on what kind of uses of the structure, we can determine what is the live load acting on the structures. So for example, for a self-contained dwelling like houses, the live load, as you can see, is between 1.5 to 2 kilopascal. Again, for simplicity, we consider that the live load is distributed over the area, over the floor area, and the unit is kilopascal here. Right. For the general areas like kitchens, laundries, and stuff, we take it as 1.5 kilopascal. And stairwells and other areas like balconies and stuff, we might be taking as 2 kilopascal. So that means this is the load that is distributed over the floor area. So the load is distributed like 2 kilopascal or 1.5 kilopascal. Now, for other areas like offices, as you can see, for general office spaces, we take it as a 3 kilopascal, and if it is a factories or industrial floor, we can go 5 megapascal as well. So depending on what is the purpose of the structure, your live load that we take will be different. And table 3.1 in AS 1170.1 gives us the guidelines on how to choose the proper live load for depending on the type of the structure. Apart from the dead load and live load acting on a structure, there can be other different kinds of load acting on a structure as well, and one of it is wind load. So as we are in a tropical environment here in Townsville, so wind loading is a quite important part of the design that we have to consider while designing a structure. So the general procedure of wind loading, calculation of wind load, is that we first find out where the site is and what is the wind speed at the site. Then we find out the design wind speed, and then we find out the design wind pressure and distributed forces because of the wind on the structure, and then we calculate the wind actions there. So this the part wind actions will be covered in week 3 to 5 by Professor John Ginger. And as you know, we are in a tropical environment and we have to design our structures to withstand extreme cyclonic wind loading as well. So this, as you know, this is QCB Stadium Townsville, which was recently built. And for designing this stadium, of course, we have to consider the wind loading on the stadium itself, and you can see it has a very unique roof structures, and we have to make sure that it can withstand the cyclonic wind loading on it as well. So to calculate the wind loading on the stadium roof, JSU Cyclone Testing Station built a 3D model of the stadium and did the testing on the wind tunnel to find out what are the wind pressures that can act on the roof structures, and then use that one to find the wind loading on the structure. So the structure was designed based on the input from the data from the wind tunnel testing. And as a part of CS2003, you will be doing a practical in the wind tunnel and see how to find the wind pressures using the wind tunnel. Another kind of loading that the structure might be subjected to is a snow loading. And snow actions or on roof and ice actions has to be considered for structural design which is subjected to snow loading in the cold countries. Now we don't have snow in Townsville, so we don't need to consider the snow loading for design in most part of Australia. And apart from these loading in some seismically active areas, we have to consider earthquake loading when designing the structures as well. During earthquakes, as we know, the ground shakes, and this ground shaking causes inertia-induced forces on the structure, and we have to make sure that the structure can withstand these forces. In extreme earthquake loading conditions, perhaps we might not be able to design the structure not to be damaged, but we have to make sure at least that it doesn't collapse and cause hazard or health hazard to the occupants. So it at least has to withstand and not collapse during these extreme earthquake conditions. So the basic procedure of earthquake design is that you need to know where you are designing the structure, and you need to know what is the importance level of the structure. For example, if it is hospital building, your structure is quite important structure, and make sure that it doesn't collapse during the earthquakes. And you need to know what is the probability factor of the hazard factor in that area. And then you also need to know the site conditions. What is the site condition of where you are constructing the building, and then that will give you the earthquake design criteria. And based on that earthquake design criteria, you will do the seismic design of the structure. So here is a video of a full-scale testing in a structure lab in Japan, which simulate the earthquake loading, and you can get a sense of what kind of loading the structure is subjected to when there is an earthquake event. So during the life of a structure, the structure will be subjected to multiple loads as well, like dead load and the live load is acting at the same time, and there might be a wind load and earthquake load coming in as well. So we have to consider the combination of different load conditions on a structure and find out the extreme possible load conditions and make sure that the structure can withstand that extreme loading conditions. And that's where we do the load combination following AS 1170.0. Now for the structural design, AS 1170.0 gives us various load combinations, and that is to simulate the extreme maximum load condition that the structure might be subjected to. And these are the load combinations that the code prescribes. So if there is only dead load acting here, we consider the load combination 1.35Z. And this is 1.35 is called as the load factor, and it is used to simulate the extreme loading conditions in the structure, and G is of course the dead load here. So only the structure is subjected to only the dead load. We are using 1.35 load factor on the dead load, and when the dead load and live load are acting together, we have to use this load factor. That means we have to use 1.2 G. G is the dead load and Q here is the live load here, and both of these loads are acting together, right? And apart from that, we also can have the wind load acting as well. So that in that case, wind load is also taking into account here. And if it is earthquake loading, we have this earthquake loading taking into account as well. So earthquake loading, if it is earthquake loading, we have EU taken into account as well. So we'll come to the load factors in the next video, but just remember that the structure might be subjected to combination of load conditions, and we have to use all these load combinations to see which one is the extreme load condition, and then we use that one for the structural design. And in this equations, you can see that these are the long-term GIL, and this GIL is a long-term factor, and GIC is a combination factor. So what it basically is looking at is if you have a if you are considering a long-term live load, then we consider XIL factor, taking into account that there is a less probability that the extreme dead load and the extreme live load will occur when we are considering a very long period of time. So we have to use XIL in that case. And when XIC is used when we are considering the wind load, live load, and the dead load, all of them reaches at extreme peak at the same time. It's a bit unlikely for that case, so what we use is XIC factor to take that into account when we are considering all three of that into account. So these short-term, long-term, and combination factors are given in table 4.5 in AS 1170.1 here. So depending on your structural type and your structural member type, you have to use what is your GIS short-term factor, GIL, or GIC factor. So we'll see how to use this factor as we come there. What we have discussed so far is a strength design. That means the structure has to be strong enough to withstand this extreme loading condition. That's why we use these load factors in there. But for the serviceability, which deals with the day-to-day functioning of the structure, we don't have to use the load factors, but we still have to use the combination of the different load types. For example, as we can see here, if the dead load and the live load is acting together, we have to add the dead load and the live load together. And if the wind load is acting, we have to use that one as well. But we do not use the load factor in it. Remember, in the strength limit state, we use 1.35 G. So this is the load factor, which we don't have to consider when we are talking about the serviceability limit state, because it is not the extreme loading condition we are talking about. It is the day-to-day loading condition we are talking about. But we still have to use the combination of dead load, live load together, or just the dead load as well. So we need to consider that. Again, we will be doing these ones as we go on. So we'll see how to use these ones.